Hi guys, my name is Anand Krishnan and my partner is Stancill. Today we're going to be showing you our electrolytic cell. We will be taking you through the process of building the cell, showing how it works, how to measure the current that the cell generates, and some common uses of the cell in the real world. The types of reactions that drive cells like these are called redox reactions, and they rely mainly on the transfer of electrons between different elements. And we measure this transfer as current.
First off, let's define what an electrolytic cell actually is. It's essentially an electrochemical cell that requires a source of direct electrical current to drive the reactions in the opposite direction. In an aqueous cell, such as the one we're building today, these electrodes will be immersed in an electrolytic solution composed of charged ions and distilled water. These electrodes, however, do not need to be metal, as they simply must be able to conduct electron flow. Today, we're using graphite. Unlike an electrolytic cell, there also exist such cells as galvanic or similarly called voltaic cells. This type of electrochemical cell does not use an external power source such as a battery and has redox reactions occurring spontaneously with a natural transfer and flow of electrons. Thus, galvanic cells have a negative delta G or Gibbs free energy change, so they have a positive standard cell potential, contrasting the electrolytic cell. Let's now take a look at the many materials that we will be using to build this electrolytic cell. As you can see, we have potassium chloride, which is our salt that will provide potassium and chloride ions, distilled water for the aqueous solution and to help dissolve the potassium chloride, the color indicator phenolphthalein, which turns clear in an acidic solution and pink in a basic solution, as you will see later, 2 pencils whose graphite will be used as the electrodes of the cell, a 9-volt battery which will provide the aforementioned direct current needed to drive the cell reactions, a stirring rod to help agitate the solution, a scupula for transferring the solid KCl into a beaker, and this beaker will of course hold the solution, and lastly we will be using a voltmeter for measuring electrical current as the reaction proceeds. To put into context, let's look at what this cell will display. This cell, having an aqueous solution, will have 2 independent redox reactions occurring simultaneously. First is the reduction of potassium ions and oxidation of chloride ions. These half reactions compose the full reaction shown toward the bottom, which produces solid potassium and chlorine gas. Next is the electrolysis of water, which yields oxygen and hydrogen gas, and the hydrogen and hydroxide ions that reform water. To balance the transfer of electrons, we have adjusted molar ratios, but note that the standard reduction potential does not change for either reaction. It is also important to know that in electrolytic cells, the cathode is negatively charged and the anode is positively charged as a result of the external power source, the battery, flooding electrons to the naturally more positive cathode, making it more negative and the anode positive. Electrons are flowing still from cathode to anode as the electrons are transferred from water and chloride to the anode from the solution. Now to the actual setup. We start by making a solution of potassium chloride and distilled water by adding solid potassium chloride to the beaker using the scupula. Next, we will add enough water to fully dissolve the potassium chloride into its respective ions, along with the stirring rod, which helps to agitate the solution, increasing the rate of dissolution. When fully dissolved, we will attach the pencil apparatus to the copper wire so that the battery is connected to each graphite electrode. We have to ensure that the copper wire and the graphite are directly touching. Simply because it was easier when constructing, the pencils are crossed so the reactions shown before in the diagram occur at the opposite side. We will then add some color indicator phenolphthalein to the solution in the beaker. As you now can see more clearly, as the reactions proceed, the colors in the solution do indeed change. As a result of increased hydroxide concentration, which creates a more basic solution, the phenolphthalein turns pink in color, and the chlorine gas produced adds a slight green-yellow color at the anode. Here, you can see the chlorine and oxygen gas bubbles forming at the anode and hydrogen gas bubbles at the cathode. Also, you can see a reduced pink color as a result of hydrogen and hydroxide ions combining to reform water as time progresses. To measure the amount of current flowing, we can use a voltmeter and attach it to the external copper wire.
Although our measured voltage value fluctuated heavily, we were able to calculate an average current at about 7.8 volts, give or take a little bit. Since we used a 9-volt battery, we obviously had some discrepancy between our actual and our predicted voltage values, so we had to calculate percent error. By taking the difference of 9 and 7.8, and then dividing that answer by 9, then finally multiplying by 100 to get a percentage, we were able to see that we had a 13.33% error in this experiment. That basically means that our actual value was 13.33% lower than what we predicted. This could be attributed to the condition of the battery, maybe it wasn't in 100% health, the temperature of the room, because we might not have been at exactly 25 degrees Celsius, which is 298 Kelvin, or it could be the fact that we measured the voltage a minute or so after the cell initially began to run, which may have caused the voltage to decrease. Like we said before, electrolytic cells like this one are meant to generate a current via the flow of electrons, but they often produce solids and gases as byproducts. In this cell in particular, we observed hydrogen gas and chlorine gas being produced, but there was also some solid potassium. However, there wasn't enough of it for us to observe it with our eyes, but that it's still there. The solid produced is especially important in the uses of an electrolytic cell commercially because it can be used to electroplate certain products. This gives them increased durability and resistance to corrosion because of the extra layer of deposited solid on their surface. And most common household items that have metal are electroplated. This type of cell is also what is used in rechargeable batteries, so you can thank electrolytic cells for your phone being able to charge. However, these cells do not produce much usable current because they require so much energy to function since they have a negative cell potential. This means that their overall Gibbs free energy, or delta G, for the redox reactions in these cells is positive, and that means that they are not thermodynamically favorable processes, and thus they do not occur naturally. This is why, as we showed in our experiment, we must attach the electrodes to an input source, the battery which supplies electricity, instead of to an output source which would take in electricity, like a light bulb, and that's what we would do in a galvanic cell. Thank you to everybody for watching this video. We really enjoyed making it, and we hoped you learned something in the process. Bye-bye.